Hello and welcome to the Build a CubeSat course. My name is Jack, and I'm one of the TAs for the course. Over the past 4 weeks, students have been learning about, researching, and building CubeSats, which are nanosatellites about the size of a softball. This year, our science mission was provided by Dr. Colin Ward from Woods Hole Oceanographic Institution. As human consumption and waste levels continue to grow exponentially, more and more plastic is being swept into the ocean. Under the harsh sunlight, this plastic decomposes from large pieces to nanoparticles, which pose a serious threat to the health of critical sea life. Dr. Ward proposed using low Earth orbit CubeSats with ocean imaging cameras to track the location and movement of ocean waste. Regular ocean imagery would inform plastic cleanup efforts and advance scientists' understanding of plastic breakdown. The students worked in teams to build model CubeSats that demonstrate this ocean imaging mission to track plastic pieces as they decompose over time. Each team member took turns moving their CubeSat in a mock orbit over several targets, while capturing images and sending them back to the ground station for analysis. Today, each team will present their findings and plan for developing a full CubeSat mission.
Welcome to the Build a CubeSat final event session, and thank you, Jack, for that introduction. My name is Rebecca Arenson. I had the honor of being a lead instructor for the CubeSat course, and I will be moderating the session today. Throughout the summer, the CubeSat students have learned from experts from both MIT and Woods Hole Oceanographic Institution. I'd like to take a moment to thank all of our instructors and guest lecturers who added their expertise to our class. Joining us here live today are some of the people who were instrumental to putting together this virtual course. Let me start by introducing Paul Fucile from Woods Hole Oceanographic Institution.
Good afternoon. Scientists and engineers at the Woods Hole Oceanographic Institution are thrilled once again to be collaborating with the BWSI Build a CubeSat course. We believe that their science mission represents some of the most challenging upcoming challenges that we have ahead of us with plastics in the ocean. And it's been a real pleasure to work with such innovative teams. Thank you very much.
Thank you, Paul, and thank you for your collaboration in providing our science mission through Dr. Colin Ward. No BWSI course runs without the hard work of our TAs, and helping us run the live session today are our 3 wonderful TAs, Mary Dahl, Jack Fox, and our 2019 CubeSat course alum, Max Mazeris. Thank you to all of our TAs as well. This year, we also welcomed a guest from the University of Maine, Joseph Patton. In the next year, we hope to expand our CubeSat curriculum to Maine so more students can participate in this project-based learning experience. I'd also like to thank all of the family members who supported the students throughout the summer as they were holed up in front of Zoom for 8 hours a day. Now I'll turn it over to our students to share with you their incredible accomplishments over the past 4 weeks. As the students present about their CubeSat mission to image plastics in the ocean, please post your questions in the Q&A under the live stream. And Jack will now go ahead and share the student presentations for us. Up first, we have Astrobeever.
Hello, everybody. We are Astrobeever. My name's Hannah.
Hello, I'm Aziz.
Hi, I'm Emily McCarthy.
I'm Albert Schultz.
And I'm Nico Moldovian. To provide a little bit of background on our science mission, our CubeSat team was tasked with designing a model CubeSat and conducting a demo flight to test the feasibility of using low Earth orbit CubeSats for plastic waste detection in Earth's ocean. So CubeSats in general can be broken down into several subsystems. The first of which includes attitude determination systems. To conduct attitude determination, we use an Adafruit 9 DOS, degrees of freedom, NXP precision board. This small inertial measurement unit, known as IMU for short, was responsible for gathering data such as roll, pitch, and yaw to determine the position of our CubeSat in its current orbit. from our testing, we encountered two main problems when integrating the IMU into our CubeSat. Firstly, we found that the IMU often presented imprecise readings of roll pitch and yaw due to the presence of magnetic material near the IMU and the natural drift in readings associated with using sensors such as an angular rate gyroscope. Although we conducted several calibration tests, such as hard and soft iron calibration, to account for errors, we were unable to get past a margin of error of 5 degrees when compared to true values. This led to slight issues, which we had to account for when executing the automatic capture of images. Using what we learned from the IMU and our knowledge of the conditions of low Earth orbit, some considerations for using attitude determination systems in space onboard CubeSats include rigorously and continually calibrating the IMU, because as I said, the IMU integrated sensors experience drift over time. Moreover, additional sensors such as GPS should be added to increase redundancy. Secondly, due to the harsh conditions of space, IMU boards must be manufactured to withstand significant temperature changes and the effects of space radiation. Lastly, space-grade IMU systems must be integrated with control systems, which can include things like small reaction wheel mechanisms or miniature electrospray propulsion systems. This would enable CubeSats to determine their attitude and then use the control systems to make any necessary corrective maneuvers.
One of the next sub-processes we had to consider was data transfer, or how we were actually going to get the data that we collected on our CubeSat, i.e. location data, images, other files, and take that data and transfer it to our ground stations, our computers, and then up to another cloud storage system like Google Drive. In this project, to make it analogous to long-range antenna systems that are used for actual LEO CubeSats, we were asked to use Bluetooth RF comm serial port profiles. So after automatically connecting and pairing via Bluetooth, we are then able to directly transmit bytes of data, and thus with some encoding and decoding, we're able to send full files and images. And then once we download all these files and images from the Raspberry Pi, our demo CubeSat, to our ground station laptops, we're then able to automatically upload them to a Google Drive folder. In terms of actual results, our Bluetooth demo was generally successful, but we did have quite a few issues with base compatibility and setup, even though everybody followed the same steps, we got very different results from person to person. In terms of the considerations for data transfer protocols for an actual LEO CubeSat, we would recommend lots more testing and protocol redundancy to help with troubleshooting and more fail-safes. We would also like to consider more sources of interference and managing our downlinking windows and rates better to ensure that all needed data can be transferred cleanly and accurately.
After we received the images, we needed to process them. Here is a general outline of how the image processing worked. In its simplest form, it took the image, modified and improved it for ease of processing, and then counted the pixel and found the results. Next slide, please. These are some example photos from our first flight tests. The center false color image is a representation of what the software thinks of the image. The rightmost image is the output used for counting the pixels and representing the results. It also helps the plastics show up more clearly. Next slide, please. The main sources of error for us were the image quality and characteristics, such as blurriness, lighting, and resolution. Shadows, glare, light reflecting off the shiny plastics, and tint of the plastics also proved an obstacle in some cases. For example, tint can cause blue to appear greenish and get wrongly classified as green. On a real CubeSat mission, this would be feasible, but significant improvements would be necessary. Because of the relative pixel sizes of the floating plastics, possibly on the order of only several pixels, the code would have to be made much more powerful. This could involve using another more powerful Python library, such as OpenCV, or even incorporating AI and machine learning into the image processing. Having a very high resolution camera would also permit better plastic identification, but such a camera would be impossible to fit on a CubeSat.
Based on our testing and the demo we conducted, we came to the conclusion that science mission is definitely feasible. Through our image processing, we showed that we can identify plastics on a plain background, so we would be able to identify the plastics in the ocean. Our communication system was also successful for our demo, though it did take a lot of time to get connected to each time we booted up our CubeSat. When we ran the software properly, it worked correctly. However, it was very difficult to run correctly in our short 90-second window for booting up our CubeSat before we began our orbits.
The demo helped us learn a lot of valuable lessons for future missions and projects. The first was to test early and often. And when testing, make sure you test exactly like you were going to fly, so full integration of your system can be tested. You also need to make a plan and know when to let go of one that isn't working. For instance, we had an original plan that we ended up having to modify because we realized that it was not going to work for our mission. You also need to assign roles so that every critical function is accounted for. Make sure the basics are working first. Don't try to overcomplicate things when it isn't necessary. And finally, communication is key. This is even more important in a virtual setting when things can be misinterpreted when you're not face-to-face with your teammates. And that is all. Thank you.
Thank you, Astrobeever, and great job. How did you change your plan throughout the process?
One of the biggest things was we had initially, we're going to downlink our photos directly to GitHub, but a lot of people were having issues pushing to GitHub. So we ended up changing so that the images and telemetry packets would be downlinked to Google Drive.
Great, thank you. Next up, we have Buzz Lightyear.
Hi, we are Buzz Lightyear. I'm Emma.
I'm Josh.
I'm Ben.
I'm Claudia.
I'm Joshua C. And today we're going to be presenting our CubeSat mission. So for our results and successes, one of the major results was that we built the CubeSat structure. On the right, you'll see our CAD model, which we have all our parts, and we use this design to simulate our orbits and take pictures. Our ground station, which is our computer, was able to receive image data and telemetry package, which are location and time, from those orbits, and it was able to process the image data that we received into statistics, such as what color the squares are, how many there are, and what size they are.
And of course, with this kind of project, we of course ran into some stumbling blocks and problems. By far, our biggest source of problems was our Bluetooth communication system, because Bluetooth is a black box protocol that we can't really control. So it's very sensitive to changes in system, changes in configuration, changes in hardware. And so even if we ran the same exact steps on different people's machines, some would work, some wouldn't. Some would work sometimes, but then crash unpredictably. And generally, it just held up our process a lot because we couldn't get the same thing working on everybody's system. Our position sensing with our IMU also had some challenges. We were using a magnetometer for our position sensing, which of course can be influenced by nearby objects with magnetic fields. So desk fans, screwdrivers, even like large pieces of metal can deflect magnetic fields. The other option would have been to go with cumulative gyroscope measurements, where each time through our control loop, we record how much the satellite's rotated in that frame and then add that up over time. The issue with that is that it's very easy to accumulate error, because if you're off by 1 degree every frame and you're running 100 frames per second, you're going to go through a full circle in about 3 seconds. We had only minor errors with our battery power tracking, mostly down to the fact that we're only using a few percentage points on our battery, and our battery only records in full percentage points. So if we flew a flight and ended up with a 2% battery drop, we had no way to know if that was 2% in almost 3 or just barely more than 1. So we got a few inconsistent results from that. Another big issue was our environment. Lighting was very different in our different locations. As before mentioned, magnetic fields were different. And since we were using a human-propelled orbit, the orbit was a little different every time. So it was hard to standardize to exactly what we were flying. And of course, with a project like this, time constraints are a big thing. We ended up not having as much time as we would have wanted to test and troubleshoot our various subsystems before we had to integrate them. So when an error popped up, we didn't always know which subsystem it was coming from.
So what did we learn from all the problems we encountered? Well, we learned that we need to test the individual components of each system before integrating them together. Now, in theory, this doesn't sound so difficult, but what Ben just said was that we were trying to integrate code together that wasn't fully functioning, which meant we were spending time trying to troubleshoot and work backwards. On the right, you'll see a flowchart. Now, you can't see all the individual components of the flowchart, but you can see that if one individual component is messed up, it disrupts the whole flow. This caused issues, and it caused us to spend time on things that we should have been doing earlier. Additionally, we needed to have established backup plans before the final tests. A big problem we ran into at the end was that IMUs weren't calibrating or weren't connecting to the Pi. This meant that Joshua had to go back and write code right before the end, which was really pressuring. Lastly, we needed to consider the variety of ways to accomplish tasks and determine which was the most effective. If you watched the videos of all the groups this morning, you would have noticed that everybody did things differently. We really needed to evaluate which methods were going to work the best for us, which we didn't always do. This meant that down the line, when it was too late to go back, we were realizing that some things weren't working effectively.
So some other lessons that we learned. So we learned that when creating a software interface, we needed to have team members work even more closely together than we were already having them work. For instance, between our ground station and our CubeSat, we had troubles trying to get them to communicate to each other simply because the code was not synced. So we didn't know what data was being pulled off the CubeSat. We didn't know how that data was going to be received by the ground station, and communication could have definitely helped us in those circumstances. We also had trouble trying to integrate our IMU into our overall flight code. It was unclear about what values were being pulled off the IMU, how they were going to be used in the flight code as a whole. And again, communication could have helped us significantly there. On the topic of communication, we did have some form of documentation. However, it wasn't as detailed. It wasn't as up to date as it could have been. So if we had put more effort into maintaining that, that would have solved a lot of our problems before they even came to fruition. Time was one of our biggest challenges, as we mentioned earlier. So if we had created a timeline with concrete deadlines, we could have been able to expect things to be done instead of just waiting for them to be done as the project progressed.
But despite our many challenges, our mission still had a lot of real-world applications and impacts on future missions. So if you remember what our science mission was, it was to serve as a proof of concept for the Woods Hole plastic imaging mission. So our mission served to prove that this mission could be feasible. We tested different types of downlinking like Bluetooth. We created a working model to inspire the design of future satellites. We also informed timeline decisions for future missions to decide how long they should spend on each system. And our model of testing of our CubeSat could be a very good model to test for future missions. And finally, a lot of our code could be easily applicable to future missions, such as how we took images or our concept of the IMU, if we're able to tweak the way that it takes measurements. And that is the end of our presentation. Thank you very much.
Great job, Buzz Lightyear. Sam asks, because of the short time schedule, was there anything you had to cut out or reduce in some way for the final CubeSat system?
Yeah, we did have issues with that, especially with our Bluetooth communications. Once it was clear that Bluetooth was not going to work on some computers, we just had to scrap communications altogether and store images on the CubeSat to be retrieved later. We also had to cut out our graphical user interface simply because we needed to focus on other things. And with the time constraints, it was just impossible to have done by flight day.
Great. And then Nidhi asks, what would you alter in your testing process to make your integration go more smoothly?
Well, what we ended up doing was we were rushing to integrate everything together. So we ended up trying to put together code that wasn't fully functioning. So what we needed to do is just have that code completed before we were integrating it, because once you start integrating, it's harder to troubleshoot, which ended up being a pretty big issue for us.
Great. Thank you, Buzz Lightyear. Up next, we have Oddsat.
Hello, we are Team Oddsat. I'm Madeline Robertson.
I'm Neri Hong.
I'm David Wong.
I'm Brooke Ablis.
And I'm Graham Wilson.
The first of the subsystems is the IMU. The goal of the IMU was to tell the camera when to take a picture. We started off with the initial goal of telling the camera to take a picture every 120 degrees, starting at magnetic north. However, we realized that that wouldn't end up working because the IMU just wasn't precise enough and there was too large of a margin of error. Instead, we determined what the yaw was for magnetic north, which differed based on where each team member was located. After, we input our values into the main code to run it. Then, the IMU code waited until it got to magnetic north to take the first picture. After that, the main code waited a total of 20 seconds to take the next picture until the CubeSat had completed 3 orbits for a total of 9 pictures.
So once the images are captured and processed by the Pi, they need to be downlinked to the ground station. To complete this task, we implemented the Bluetooth RFCOM protocol. Bluetooth RFCOM is a serial port emulation tool that allows 2 connected devices to exchange bytes of data back and forth. For this project, image data is encoded to bytes and sent from the Raspberry Pi to the ground station, which in this case was the user's personal computer. Once received by the ground station, the incoming bytes are decoded and written as a JPEG image. As for our team, every member was successful in data transmission. However, there was a problem with decoding. The incoming data was incorrectly written to the hard drive, which resulted in a corrupted image. These images were unviewable unless uncorrupted. Using a program from Distuna, images were able to be uncorrupted and the damaged data about 35% of the time, so not ideal. And during the flight day, an unexpected error occurred, which caused all images to appear to contain no data, which displayed nothing. This was an unusable image and a certain place for improvement in the future.
In terms of the ground station was able to successfully upload the files to Google Drive during our test run. However, the Bluetooth decoding did not work as intended as stated before on the CubeSat, which caused all received data to be unusable. Although we made a GUI, it was not used during the actual flight due to lack of time. And the ground station could be something that we could work on a bit more in the future and integrate better with Bluetooth.
So for the image processing, in the main code, the image processing steps are integrated so that enhanced images with their statistics are provided. Ideally, this is the image processing progression that should have automatically happened in the main code. And each individual steps are uploaded to the Google Drive for remote members to access. All the files should also be saved on the Pi, and during the flight, this did work well. However, because of imperfections in the image transmission, the captured images were manually processed through the scripts after flight to give these results.
Next up, we have the structure and power, what keeps everything together and gives it the power to run. The structure ended up staying together very well. It was easy to plug in the Pi to the battery within the 1 minute and 30 seconds we had before we had to start our orbits. And we did have a problem during development. We originally mounted the IMU on the top plate. However, that made it upside down, which messed with the IMU code quite a bit. So we had to fix that last minute. Power also did what it needed to do. It gave power to everywhere that needed to have power. However, the power budget was slightly off. We estimated that that the code would deplete the battery about 2.5%, meaning that depending on how close your battery was to already changing, it would be 2 or 3% depleted by the end of the 10 orbits. However, on actual test day, it seemed like it was closer to 1.5% because we had most members get 2% depletion and 2 even get 1% depletion.
So what did we learn? Well, definitely need to test much more frequently and much before the day before flight. Implementation of the code into every system is definitely necessary, and having backup code to make sure that if something goes wrong, that the mission isn't a complete failure. Backup code definitely needs to be implemented. Also, communication between team members is necessary for a successful project because we had overlapping variable names in our code, which caused errors when it would run. It would get confused. So we need to make sure that we communicate better about our code and how to integrate within system.
Although for this mission,
For this project, the mission was feasible with the Raspberry Pi, and concepts of each subsystem is definitely applicable to the real missions. There are many improvements that needs to be made for the future. Within the actual subsystems, the IMU, as mentioned before, was not accurate. So because of its unreliability, this hardware would not suffice in real missions. The Pi camera is also not ideal because of its limited resolution and picture quality. Although in our project, there was no major problem with blurriness, in real missions, the Pi camera would not pick up any details because of distance. For image processing, the scripts were written based on one person's flight setup. So as the person in charge of image processing, the enhancement codes were made according to my own flight environment. So things like the brightness and light that are conditional to each member's flight setup could have been better accounted for with more testing and data collection before the actual flight. In real missions, the image processing scripts that use tools such as OpenCV and BGR values are not really optimal and would not be great, but it should be developed for accurate results. Obviously, the Bluetooth did not work 100% of the time. Although sometimes for some systems it might have worked, it was very difficult to figure out in general. Guaranteeing it to work on flight day for everyone is especially difficult because different members had different combinations of computer systems. In real missions, the speed of Bluetooth is affected by distance, so this would not be the ideal way to transmit images.
Thank you, Oddsat. Great job. So we have a question from Avik. What sort of factors influenced your CubeSat structure and design?
Well, there were a few things. First of all, the pieces we were given. We weren't able to use anything that all of us didn't have. So that includes any machines for making adjustments or most excess materials. Also, the battery and the Raspberry Pi, we both wanted to be on about the same plane because the battery was fairly heavy. We didn't want it falling and crushing the Raspberry Pi as it was only held on by Velcro. And also, we only had a limited amount of space and weight because a 1U CubeSat can only be 1.33 kilograms.
Great. And we had several questions about your IMU, asking to go more into detail about how your IMU code was developed and how would you improve the existing IMU, or do you think that you need different hardware?
Basically, I feel like the best way, I saw a question where it asked, what do you think would be the most ideal way, time-based or position-based, to take a picture in like a real life situation with a real satellite? I feel like position definitely would be better because it is like the main goal of what you're trying to do. But I feel like using time as a backup to like if the position failed would be the most accurate way to go about that. And the reason why the code came to be was extremely last second because we realized that no matter how good the code was, the IMU that we were given just was never going to be precise enough to get the exact measurements that we needed for position-based code. So we ended up integrating a bit of position, but much more of the time because that was most accurate given the materials that we were given.
Great. Thank you, Oddsat. Next up, we have BYJ Cube.
Hi, everyone. We are the Beastern Yellow Jackets. My name is Catherine Tan.
My name's Nick Leon.
I'm Jameson Ma.
Hi, I'm Navy Walker.
And I'm Winston Tang.
The photo shown here is of our CubeSat, which we named the BYJ Cube. Our goal for this project, which was also our initial expectation for the flight, was to have the CubeSat and the ground station work together to determine the percentage of plastic sheets, the amount of each size plastic sheet, and the percentage of each plastic sheet color on all 3 of the white poster boards while orbiting for 10 minutes. Next slide, please. After we developed a design review that included budgets and a concept of operations, we wrote code that used the IMU to calculate our CubeSat's orientation in space, code to transfer files to Bluetooth, and code for image processing. We've compiled here a few lessons that we learned along the way, as well as future applications for an actual CubeSat mission. Now, Jameson will first present our results for flight day.
So here are our flight day results. So one person was able to take images for 7 out of the 10 orbits and were able to downlink all of them to their computer through Bluetooth during the orbit automatically. One person was able to take all the images except for the third image in the last orbit, which got saved to their Raspberry Pi and then got downlinked to their computer after orbit. Another one of my group mates had an IMU issue during orbit. I believe it was an issue with yaw measurements, and for clarification, yaw is the rotation about the vertical axis. And the last two of my group mates had everything working during testing, but were unfortunately unable to access their Pi within the 1 minute and 30-second setup time due to Wi-Fi and SSH issues.
So now that we've talked about what we did on flight day and what we developed, we're going to discuss a couple of the lessons we learned and how we can apply these lessons to possible future CubeSat missions. One of the major lessons that we learned was that technology is extremely sensitive. Specifically, the IMU that we used contained an accelerometer, gyroscope, and magnetometer. Essentially, the entirety of our CubeSat mission was based upon the IMU being able to detect the position of our CubeSat. However, as Jameson mentioned before, I was unable to use the IMU to do so. Therefore, in a real CubeSat mission, it becomes extremely important to test the hardware that we are given to make sure that it is actually able to serve the purpose that it has. We specifically had 3 technologies that we needed to ensure were calibrated and tested thoroughly to ensure that our CubeSat mission was successful. The first, as I mentioned, was the IMU that had to be calibrated. After magnetic influences, the magnetometer did not always necessarily give correct results. Because of this, our CubeSat mission would be greatly affected. In future CubeSat missions, backup systems must be created in order to provide various sources as to how the CubeSat can determine its position, especially for a mission like this, where image processing and determining where plastic is located on Earth is extremely important. It's important to ensure that the technology that we have is precise and accurate. Another one of the technologies that we had to test a lot was the camera. As a result of us working in different environments, the lighting and our camera's sensitivity to lighting altered greatly between each of our different environments. Thus, when developing image processing code, it became extremely important that we calibrated our camera as well as our code to make sure that the images were processed correctly and correct plastic statistics were given. Again, in a real-life CubeSat mission, image processing would have to take into account various external environmental factors that would affect the quality of images taken. Lastly, battery power functionality was something else that we had to keep into consideration. Unfortunately, the environment didn't allow us to use solar panels. Therefore, we only had one power source. However, in a real CubeSat mission, it would be essential to have multiple sources of power to make sure that there would be enough power for all of the critical functions. And this leads into testing. Because we know that technology is so sensitive, to make sure that it will work when a CubeSat is actually launched into space, we have to test a lot. Specifically, theoretical application of a code or a program does not necessarily equate to the practical application. Therefore, the testing that my team did was done in 3 stages. First, we tested individual critical functions to make sure that A, the camera was able to take pictures, the IMU was able to detect location, and then that the CubeSat was actually able to downlink this information to the ground station. Then we did partial integration, where we tested interfaces and related subsystems. And lastly, we did whole integration, mimic what would occur on flight day. Again, this is extremely crucial on a real CubeSat mission, again, because of sensitivity of technology and to ensure that nothing goes wrong while in space or that there are backup systems when we do go to space. Now, Nick is going to talk about image processing.
As Nidhi mentioned before, image processing is a very important aspect of this project. Image processing must take into account to all the different environmental factors to maintain accuracy. In our specific mission, we were able to calibrate our things. So with lighting, weather, and positioning. Lighting affected the brightness of the image. Weather could affect the camera's ability to take quality images. Positioning affects the field of view of the camera. In a real CubeSat mission, we must make sure to take these environmental factors into account. Now, Wenson will talk about communications.
Finally, we have communications. CubeSats need to be able to downlink information to ground stations efficiently and consistently. What we learned was that backup communication systems were essential. For example, one of our team members' Bluetooth driver became corrupted the day before our flight day. We also had compatibility issues. The Mac operating system worked much better for Bluetooth file transfer than the Windows operating system did. Backup communication systems are critical in preventing mission-ending failure because if you send a CubeSat into space and lose communications with it, the CubeSat is essentially useless and is now a piece of space junk. Another aspect of communications that we worked on was automation. Automating the process of sending images to our ground station without human control was one of our critical functions. Automating across multiple operating systems proved to be a challenge, especially on a short timeline. Future missions need to be able to downlink consistently without error to ensure mission success. In conclusion, over the course of 4 weeks, we learned so much about planning and executing a CubeSat mission. We learned about the many factors that played into the mission success, sometimes through trial and error, and we learned the importance of teamwork and collaboration. Thank you to all of our instructors and TAs. Special shout out to Jack Fox, one of our 3 awesome TAs. Thanks for watching.
Great job, BYJ Cube. I have a question from Mary. How would you take environmental factors into account on a real mission?
I think that would primarily be done in a couple of ways. First, we would need to have backup systems, ensuring that hardware wouldn't necessarily be affected by these external factors. For example, if you had multiple cameras, then if one camera wasn't able to sustain or take correct pictures, you would have backup systems. Second, communication would be important in terms of making sure that if there was some sort of environmental factor that would affect the quality of images taken, there would be communication done to alert the CubeSat and ground station that there was some sort of an environmental factor that would do so.
Great.
To elaborate, if there's like clouds over the ocean that are blocking our view of what we want to see, we basically kind of have to wait.
Yeah, taking into clouds into effect is not something we had to worry about, but a great point. We have another question from Michael watching on the webcast. Do you think position accuracy could have been improved if you had multiple CubeSats communicating with each other?
Yeah, I think a constellation of CubeSats would work very well in this type of mission, so they could all communicate together, and also you have more redundancy in this case.
Great job, BYJ Cube. Thank you. Next up, we have Rubble Space Telescope.
Hi, I'm Sam.
I'm Sajeev.
I'm Kat.
And I'm Hassan.
And I'm Vanya.
So our results on flight day, all members of our group were able to successfully take images, process those images on our CubeSats, transfer those images and the telemetry data that our CubeSat I was able to collect while taking the images down to our CubeSat. We were able to do this through Bluetooth. Unfortunately, we were not able to get our code to run when we on boot, so we had to manually set up our CubeSat and all of its code every time we wanted to test our system.
All right, so these are the main challenges we had to face throughout the whole process, and very similar to the other groups, Bluetooth was one of our major problems. Different computers have different protocols, like Bluetooth might work better for a Mac or Windows or different versions of the same kind of operating system. And Bluetooth is not well documented at all, so it was really hard to find a protocol that would work for everyone and to communicate that with everyone in the group. Time management or organization, as other groups also said, we were on kind of a very short time schedule, so kind of making everything work on time was a big challenge. And since the CubeSat is such a complicated system, it's made up of different subsystems, it takes a lot of communication and organization to kind of coordinate everything to make the final product. Sensor inaccuracies, the IMU can be inaccurate. No matter how good the software is, it's still going to rely on the basic data you get from those sensors. And there's different environments for image taking, like different lightings and backgrounds, blurry and unfocused images that can affect image processing and the data you get back in general. So how we overcame these challenges. So for the Bluetooth compatibility, we found a protocol that worked on 4 out of 5 of our group members' laptops. And in general, just working together and helping each other out through the whole process led to success. So that we didn't leave like one person behind or just only get our system working. For the time management and organization, we at first did individual work, and then in the end put everything together and made sure to communicate to everyone. And throughout that, clear communication and documentation, like how-tos for building stuff and how-tos to set up the code, were very helpful. For the IMU inaccuracies, we calibrated the IMU for each person and used different functions of the IMU to complement each other and kind of create redundancy in the system so we're not relying on one function of the IMU. For the different environments for image processing, we set color ranges based on each person's environment using test images that they would use so we can know exactly how their camera picks up colors and lighting. And we tried to make our image processing code take into account different brightnesses in different environments.
So from our flight day and our test results and taking these challenges into account, things that we would do better next time. For one, we would try to develop and test our image processing earlier and try to figure if we can find something better. Because while our image processing software did work, it was very inaccurate. We would also like to plan more tests in general so that we can revise our work and look everything over and make sure integration goes more smoothly than it did for our test. We also would like to include more fail-safes within our software, trying to think of more edge cases and things that could go wrong and try to account for that better than how we did. And then time, of course, was still a big issue. We would like to be better at scheduling our time and making sure that everything gets done on time so that integration goes more smoothly.
So a couple of things we've learned are that firstly, technology can be sensitive and require redundancy. So in our case, the IMU would give sporadic values and it would be hard to work with. Secondly, it's important to have a foundation and to make sure you establish some results and like the minimal goals before you start reaching out for like higher functions. And the third thing is that we need to account for everything that will go wrong because it probably will. And the last thing is that we need to make sure our team understands all the different systems and how they fit together.
All right, so now we're going to talk about how our learnings can be used to or implemented in a real CubeSat mission that the Woods Hole Oceanographic Institution would use.
So, of course, a real mission would require a lot more sophisticated subsystems. Firstly, instead of using an IMU for a real mission, we would use GPS to ensure that the data about the satellite that's being collected, like speed, bearing, and orientation, would be much more consistent and accurate. Next, we would use a powerful camera like a panochromatic camera that's commonly used in satellite imagery missions to take very high resolution pictures. And finally, we would reinforce the structure of our CubeSat by building it out of special materials that will protect the satellite from harmful solar radiation.
And lastly, as everyone's mentioned before, we would definitely use many different types of image processing. Simply just using an RGB camera probably won't be enough, considering that a low Earth orbit satellite will pass around Earth 16 times in just one day. So considering it'll go around many different lighting conditions, it would be important that a specified object detection and identification algorithm is used so that the Woods Hole Oceanographic Institution wouldn't have to search through tons of images and would receive specified images of plastics. That's all. Thank you.
Great job, Rubble Space Telescope. And a few questions for you as well. Let's see. Max asks, what difference between your test and real space hardware would have to be addressed to make this mission successful in the real world?
Vince, try to make a space-worthy CubeSat. I think it'd be important for, we definitely would need space-grade materials. While we do have like aluminum and such that would be able to be used in space, the acrylic panels on our CubeSat that we have would not be space grade. And our camera is just a standard Pi cam, and it would not be able to take high enough resolution pictures for this mission to be feasible. As mentioned in earlier presentations, IMU as well would need to be replaced with something like a GPS that would be more accurate and able to hone in on where we need to be.
Thanks. And Mary asks, what plan would you have for increasing the amount of tests?
So I think that feeds into time management a lot. Like, I think we were trying to make our code perfect. I think a lot of functions that we tried to make in our code, we got halfway through, we didn't end up finishing them. And then we figured that we should have instead used all the time trying to develop those, which we didn't even finish, to instead test and perfect the basic functions. So instead of aiming too high or aiming for stretch goals, we should have just made sure that our smaller goals would really work.
Great. Thank you, Rubble Space Telescope. Great job. And now we have some time to open up for general questions. So These questions are open for anyone in the class to answer. We can take a few answers from different students. So first off, if you were consulting on a CubeSat for Dr. Ward that he would be proposing to send up into space for real, would you suggest that he does the image processing on the CubeSat or on the ground?
I would say that he should do it on the ground and save downlink timing.
So I would actually say it might be beneficial to do it up on the CubeSat if the power allows for it, because then they can compress images, and the downlinks, they would have to downlink basically a smaller file because they can process the images on the CubeSat and then send down a compressed version of the file and telemetry on like the location of that plastic and whatnot. And they would have also more specified data received. They wouldn't have to like run it on the ground.
Yeah, I would agree with Sajeev. If the CubeSat is big enough to house the necessary processing power to do image processing on the CubeSat itself, then I believe that would help save time for downlinking a larger quality image.
Great, great answers to everyone who answered that. Paul asks, could anyone describe the importance of ground truthing? We want to start with someone to give an explanation of what is ground truthing. Paul, do you want to chime in to start?
Well, ground truthing involves knowing the conditions that are on the ground, hence knowing the truth of what it is as it sounds, ground truthing. So in the case of ocean temperatures, we would measure temperatures at locations and compare them with our results from in space. And for plastics, I'll ask you, what would we want to know from space about the conditions that we believe we're measuring on the surface?
In other words, how would you confirm that the results you were getting were accurate?
We could image like test sites, predetermined test sites, and make sure that the results from our CubeSat match up with those that we like see on the ground. Like if we see a piece of plastic there from the CubeSat, we can go over there and look, is there actually a piece of plastic there? And by doing that, we can ensure the accuracy of the results of our CubeSat mission.
One other.
Go ahead.
Sorry, yeah, I was just going to say one other thing that might be helpful is identifying what type of plastic it is that is being identified, and like comparing that to like a pre-existing database of what type of plastics there generally are found in the ocean in large quantities. And maybe if you could also analyze what type of plastic you're looking at, then you could also understand how harmful it is to the environment and how much danger it poses to the ecosystem.
I think another thing Colin was talking about was like for sending out a bunch of test plastic. Sending out test plastic and then using currents data like in the oceans to see how those plastics move. So if the CubeSat imaging confirms that the plastics are moving in the same fashion that they're expected to based on oceanic currents, then that would be a way to confirm our CubeSat's data.
Great suggestions, everyone. And Avik asked earlier, what did you learn about working in a virtual environment and collaborating virtually?
I personally think that collaborating virtually was a good communication exercise. Generally, when we're working on engineering projects, it's definitely easier if you're there with someone to physically show them or physically test what their code is doing or how their hardware is working. But since we are all virtual and aren't able to work together in person, it becomes really critical to have very good communication skills, specifying exactly what instructions a person needs to follow. So I think although it was initially difficult to communicate with each other, overall communication skills were greatly helped and assisted as a result of having to work together virtually.
Yeah, and also I think I heard this idea from one of our seminars actually about communication, but it's kind of good to have like a moment to just talk to your teammates about something not to do with like your project or engineering, to kind of like, because in person you can like see body language, you can talk to each other, but on Zoom it can be more professional. So it's good to kind of have time out of the day for relax or kind of just know your teammates better.
I also think that as the project went on, our communication clearly became easier, as like at least my team, we had our Discord server as well as our GitHubs. We could see all the code. We had multiple Zooms outside of class just to make sure everybody had critical functions working independently. So as we got going, it definitely got easier to communicate with everyone. And we all definitely learned a lot from that.
Great answers for everyone. If you were asked to take this demo mission and convert it into a real CubeSat that you were going to launch, what would be your plan for developing that real CubeSat and getting it to a level of readiness that you felt confident launching it?
I think the very first step would be to ensure that your critical functions, basic critical functions, were working. I think a lot of us had the same issue that we tried to work on stretch goals before we worked on our critical functions. So one thing we would change if we were to actually make this a CubeSat mission would be first to plan out our critical functions, make sure those work entirely, and then move on to stretch goals. This could be done by, again, the process that we used, where we built a ConOps, made a block diagram, created budgets. Essentially, all of that pre-planning would be important before we actually jump in and start building and testing.
And I guess to go off your point on pre-planning, laying down the groundwork of assigning people roles, like I guess person A does this, person B does this, and like assigning, making schedules and laying out the groundwork for a successful project, I guess, is the foundation of a successful project, is what I'm trying to say.
Any other thoughts on how you would lay out that foundation?
I would also say that for a real CubeSat mission, the first thing you'd want to do is spend a lot of time thinking about your high-level mission requirements, and then formatting that into necessary mission critical requirements, and then stretch goals, and then communicating those requirements with any stakeholders and other people that are reviewing your proposal.
Those are all great thoughts of how you would plan your mission, and how would you go about building and testing it based on your experience over the past few weeks?
Well, one thing for testing that we should consider if you're doing an actual mission is, and I think every group came to this realization, is that the lighting was super different for different people. So there are many variables that will be different, and not all variables will be controlled, I guess. So you really have to account for the real world situations and the phenomenon that you will encounter on the mission. So I think it's important to not only have a large quantity of trials, but also greatly vary them in terms of the environment, in terms of what kind of processes you're using, and just because the more tests you have, ultimately the more streamlined your final mission can be and the greater chance of success.
Also, I think a lot of groups talked about how in the end, the implementation would be kind of hard, or the communication between different subsystems could be hard. So I think having one person whose job is to be the systems engineer that kind of communicates with everyone and makes sure everyone knows the big plan of the whole system, that would be a lot of help in the designing of a real CubeSat.
Yeah, and just to add to that, testing exactly like you're going to fly would be absolutely necessary, because we didn't all test our integrated subsystems before flight day in a set controlled environment. We had a couple individuals do it, but looking at building a real CubeSat, everyone would need to test each individual subsystem exactly as we plan to fly, and then test the integrated system over and over again the same way we plan on flying.
Yeah, and to build onto that, kind of like what Rebecca, what you were talking about, having someone purposely try to break your thing so then you know how to fix it. That's really useful, and building in redundancy so that if something unexpected does happen, it's just not a complete failure. So purposely messing up and making errors is honestly a good thing. So
great insights. So we'll end with some fun questions. Based on your experience this summer and meeting the scientists from Woods Hole, would you want to be a scientist, an engineer, or something in between?
I personally would want to be something in between. I think there's aspects to engineering and aspects to science that kind of blend together. I.e., to be an engineer, you need to have a very good understanding of basic science principles, but then to apply like theoretical applications in science, you need to have a good understanding of engineering principles. So I think something in between where I'm able to apply science, but practically apply it through engineering, I think that would be an amazing job.
I think I'd prefer straight engineering after this. I mean, definitely having to work with scientists, of course, but I think that I want to stick to the troubleshooting side of things and the figuring out what's going on and how to fix it.
Great. Everyone has their own path, and it's awesome to see you guys find that. What was the hardest challenge of your project this summer?
I think the hardest part of this challenge was getting Bluetooth to work, because between different operating systems, it would act unaccordingly, and it would be different. And we spent a lot of time working to get it fixed, but sometimes to no avail.
I would have to agree. I think that Bluetooth compatibility issues were the worst part for us to deal with. And I think that in the future, we would much rather like to use a different means of communication.
Also, just having to get stuff working on 5 different computers in 5 different locations in the US was hard. I mean, that made Bluetooth much more difficult, but it made everything else more difficult too.
Our team kind of got lucky with the Bluetooth protocol we chose, so I would say like time management, because it was like a really short amount of time, and we tried to get a lot done.
4 a.m. grind was definitely real.
Lastly, I would also say like actually communicating with people in virtual setting and figuring out a way to integrate everyone's subsystems that they're working on, and coming together to make a final product.
Great. And finally, I want to hear from everyone, what was your favorite aspect of the project?
I definitely think Bluetooth was my favorite aspect, because otherwise, if it wasn't, I would have spent all this time in vain.
I think my favorite aspect was actually getting to build a CubeSat, to be able to put the parts together to work with hardware, which is, I guess, an experience I definitely don't take for granted.
I agree with Josh, but I also really enjoyed just getting to collaborate with like all these people who have done so many cool things and getting to hear all about it. It was really interesting.
I think the best part for me was being able to, once I've put all this time into putting together this super complex system, to hit the start button and just be able to see it working. But like, that is just such a good feeling.
Yeah, I would kind of say along the same lines, like, I guess it was pretty result oriented. Like, it just felt really good that when you built your like CubeSat and you were able to take a picture and, you know, get it on your computer and run the image processing and like just see the results. That was really nice. And I also think that I personally had a lot of struggles with Bluetooth, as most of you probably know, but it was really nice because I was troubleshooting for a really long time. And then anytime that something would work for like even a bit, I would get like really excited. I mean, it would stop working after that, but like those moments like where you feel like you're getting closer to the end goal, I feel like that was a really valuable experience.
Well, I liked kind of, especially like people from other states and places I haven't been before, kind of like talking to them about like how their life is kind of different than mine, and also getting to meet people that kind of have the same passions or interests as me.
I like kind of just having that physical model at the end of the day, that even if it didn't work perfectly, like you built that, you put in the work to get that to be completed.
For me personally, it was just learning about the engineering process in like real life application, because I don't think a lot of us get an experience to start off with like, this is your mission, these are your mission requirements, all the way to actually having a flight day. And so I think it was really interesting how the engineering process works and how our mission and our design develops and changes over that time.
Well, mine isn't quite as like deep as theirs, I guess, but I liked doing the CAD and the assembly.
I liked looking at my code and seeing like how when I actually turned the CubeSat, my code like being like changing and being implemented in a physical thing.
Really enjoyed the design aspect, even though we were unfortunately not able to be in the lab making our own parts. We still had different teams come up with different models for their CubeSat, so I really enjoyed getting everything together, making it look like a real CubeSat.
I really enjoyed getting to work with all these new people and getting to know them. And I also liked watching my code run and working half the time. But the half the time it worked, it was really satisfying to see that happen.
Yeah, similarly, I really liked it when my code did work, and when it worked on other people's devices too. That was very nice.
Yeah, it was really nice to meet new people. Like, I really liked the people on my team. And it was very satisfying when everyone got their code done and we all combined it and it started working and you could see the final product. That was really nice.
I also really enjoyed the collaboration and working with so many like-minded people. I also enjoyed the hands-on experience that this program was able to give us, even though we're still in a virtual setting.
In addition to like testing the code and building the CubeSat, I also really enjoyed the lectures that the engineers and scientists gave. It's really cool to see how their work sort of translates into what we're doing.
Yeah, I enjoyed. I enjoyed the collaboration aspect the most, but I really loved building the physical CubeSat, and then that feeling that you get when you run your code after staying up till 2 a.m. and it finally works and does what you want it to do.
Yeah, along very similar lines, I really enjoyed the hands-on and like collaboration aspects of this program. But sort of in addition to that, I felt like what was really unique about this program for me was sort of seeing like through the lectures and seminars how the actual design process and building process are like formalized in industry and academia and in more professional settings. Because like in our experiences, like I assume that like everybody here has like done robotics or something like that before, and we've been sort of just, or at least in my experience, I've sort of just like winged it and done whatever we thought as a group was best. But it's been really interesting and fascinating to see how this actually like translated and formalized into real industry standards in more professional settings.
I, for one, really enjoyed this building the structure, like screwing in all the screws, and then also designing the CAD model.
I enjoyed collaboration as well, like everyone, just the feeling of work together with people who have similar passions as you, and getting to like when you're all working together like desperately to solve like a problem and you finally get it done. Everyone's working together. Yeah.
I enjoyed doing the CAD, especially like assembling all the parts that I created. So yeah, that was pretty cool.
Yeah, I enjoyed the hands-on experience and collaboration, and just even though programs and things didn't always work, just working through it together and seeing it start making progress.
Great, guys. My favorite part of the course is always to watch all of you grow and learn how to solve problems together as teams and as a class. You did a fantastic job this year. You should all be extremely proud. I know I am proud of all of you. So great job, and thank you again to all of our TAs, all of the instructors and guest lecturers who joined us this year and helped make this class what it is, even though we had to switch to this virtual format. So thank you all.
You know, I have to say that as an engineer working for scientists, it was good to watch your process, because the scientists really will rely on engineers to solve their problems. They have their ideas, but they really benefit from what we're able to do. So it's been a real pleasure being able to work with all of you. Thank you very much.
And with that, we will send you back to the main stage for the final ceremony here and say thank you again. It's been a pleasure having all of you in class. Thank you to everyone who's watching online as well. I know the students all appreciate your support. We appreciate you being here with us virtually today.